All right, looking back at the code, on the server side, we're trying to get to this e value. And we've looked up x in the database stuff. And now we're going to generate another random number. This is a second random number in the same kind of range. And we're going to say that that's e. So the value that we're going to send back to the client is just a server-generated random number. It doesn't have any meaning to anything at this point. But we're going to save it in association with Alice. So we've got a message from Alice. We're saving e. Then we're going to do this computation. And this computation, generally speaking, in this system is done on both sides. That's this stuff right here to calculate y. Both the server and the client can do this. They have enough information to calculate this. So on the server side, I have to save y for later. On the client side, it's just going to calculate it because it's got all the information at this point in time. And the computation for y is a times e mod q. So, real simple. We start out with a big int. We multiply a times e, putting it in T2. We take the modulo of that multiplication, T2 mod q. And then we add in r to get y. And when we do that, if you look at the values that are in the paper, they are there. But I'm doing this with a random value, so it adds it in. At the end of this, we have y, which is the value we really want. And that's what we're going to send back to the client this way. That's one way of doing it. I'm not certain that that's the correct way of doing it. I'm sending it back. But the client actually has all the values once it gets e to do this computation as well. So it can do the calculation or it can be sent back. And I'm not certain what the security implementations of sending it are. Either way, if I were to implement this for real, I wouldn't send the value. I'd make both sides calculate it. The less information that you send, the better off you are. So on the server side, again, we save y in our database. Now, once we've done this, we're getting close to the end here. We're going to do another calculation on the server. And as it turns out, you can send back this result before you do this calculation. Implementation-wise, I think when I implemented this for real in SRP6A, I did the calculation before I made the response because I didn't want to do a bunch of calculations in a piece of code that was in a server after sending a response back to a user. But there's nothing in this message part 2 that is dependent on sending back the response. You can send the response back. So this piece is done on the server, and this is where we're actually going to generate the verification value. And to do this, we've got to go back to the database and we've got to pull out most of the stuff. Okay, we need V, the verifier, we need E, which was the random number that we sent to the client. We need Y, which is the calculation that we did off of this. And our calculation is one of these two expressions. You notice I've written it twice here. This is the one that you see as the calculation in the actual algorithm. You don't have to do it that way. You can do this other calculation like this. And I could go through the algebra and prove it to you that those two are equivalent. The reason why you would want to do the modulo p 3 times in there on each of the pieces is because if you do it 3 times, although you have some greater chance of getting a 0 value, it's 1 divided by your random number, it's infinitesimal, it tends to keep your values smaller and the calculation goes faster. So I've done it the second way, where I've done the modulo calculation 3 times, and I do it on the pieces before they're multiplied together. Either way, you get the same result. You can factor in the modulo there. So again, what are we taking? We're taking a raised to the y times v raised to the e. And this is totally non-obvious to me why this works until you actually sit down on a piece of paper and factor this out. But the two sides now have calculated the same thing. That this is our z value is what we're calculating. We've gotten an x value from earlier. But when you factor this and look at it, guess what? These two will be equal if the person had the correct password in the first place. And only if they had the correct password. Otherwise, the modulo p here will give you something totally different and bizarre. So we do that calculation, okay? And then we send back a response, which is just, yeah. I'm waiting for you to ask me if it's valid. Okay? We do the calculation on the server. And then the ending piece of this entire process is down here. We compare x to z. And if they're equal, that comparison returns a 0. And you can say that the person is logged in. If they're not equal, then what you have is they didn't validate, they didn't have the right password to start off with. Now, some of this stuff requires that your values are relatively prime, that they're not factors. By using a big prime number and generating a smaller p-value that is from the password, we can guarantee that the likelihood of them not being relatively prime is basically infinitesimal, even though we don't know for sure if the prime number we're using is guaranteed to be prime. We do know that all factors of the prime are bigger than a 32-digit or 32-byte integer. Okay, that's the guarantee on our primes, is that they are relatively prime, not that they're absolute. And by knowing that, we know that no matter what value we hash for p in the beginning, that the result means that we're not going to be evenly divisible and it will work. So there's some shortcuts like that. And that's also why we standardize things like the prime number to start off with, is because if we do these with standard values, we have these guarantees that, well, yeah, everybody's using the same value, but we can say this about it, or we can say that about it. I do want you to sit down and go through and run this code. Okay, hopefully when you run it, it's a little tiny Go program. It runs through, you can look at the different values. If you run it more than one time, I ran it once, you'll notice that I got one value up here. If you take it and run it a second time, okay, you notice that the random generated is different and that the end values are different. Okay, in one case I had z of 50,000. Over here we've got 8,000. So each time this final value that it calculates is different, but each time, because the expressions factor properly, what you get is a unique calculation that proves the validity of the user possessing the password rather than actually comparing the password. Now, the nice thing about something like this is, as a server, you don't have the password stored. You have a number. And there's no way to get from that number back to the password no matter what. So, although I think you still want to protect that number because somebody else could set up a site with the same algorithm and the same constants and validate this user, there's no good way for you to leak usernames and passwords. You can't have happen to you what happened to Ashley Madison in this case, where they lost their database and they leaked all the passwords. Also, because this never passes the password across the wire, even if you generate the V at the beginning of registration, since you never pass the password, provided that the way you've gone from the password to that initial value is a decent hash function, there's no good way to go backwards from the hash to anything. So it protects it from that perspective also. I don't really understand why. Well, I do understand why. The reason why these kind of systems are not used more often is because they require that you have an understanding of the cryptography, and it requires multiple messages to be sent back and forth. Now, if you actually do SRP6A instead of this base algorithm, at the end of it, we have information that we can use to generate a HMAC signing key. We can do one additional hash, and both the server and the client can now have a 32-byte key. The nice thing about a 32-byte key is that that key is the perfect size to do AES encryption. So we can authenticate, never send the password across the wire, and at the end of it, we can have both sides with a key that they can turn around and do strong encryption of their data and send back and forth their data, and guarantee that nobody can listen in because they've encrypted it on both sides. Another thing that you see commonly is a big headache in websites and applications is a thing called cross-site scripting, where somebody manages to send in a script from another site and or send in data from another site. It's quite often referred to as XSS. A login system like this, when you encrypt, isn't subject to that kind of interference, because since everything would be encrypted on both sides, you never have the problem of somebody being able to plug something else in from outside. The key to that is that every bit of your encryption has to also include a basically digital signature of the encryption itself. When you go and look at these encryption algorithms, they'll have something like Gladios. It's an algorithm, or there are some other algorithms that they use on the encrypted data. And these are complex checksums that get sent with the encrypted data that guarantee that the encrypted data has not been mucked with in any way. So you've got to have some stuff like that. Now, in the encryption process, if you're going to go between a client and a server, you also want to guarantee that there is no possibility of ever factoring out the numbers. And if you send back and forth enough messages, and some of those messages repeat, you could factor out what the keys are in the encryption. To prevent factoring out the keys, what you do is you use a nonce. This is not the same nonce as in our blockchain. This is the kind of a nonce that, generally speaking, counts up, but it isn't used to change things. It's used to guarantee that there is no possibility of ever factoring out keys from encrypted data. So the combination of one of these checksums, a nonce, and your encryption and your message makes certain that you are talking to the server and the server is talking to you, and nobody is talking in between, and no man in the middle can interrupt and capture any of the information in between. And you haven't sent the password across the wire at all, ever.